So from the first part of the video, you will understood that what we are going to make. So we will make a autonomous rover, a robot that will move between two walls. And actually, when you make a rover and try to make a rover run in a straight line between two walls, then there will be some error in their straight move, like diversion will be occur in their movement. So we will control that diversion and make try to able this rover to move in a straight line. So we will use the lidar as the main perception and sensing unit. That lidar will take the data from the surrounding, the two walls on the side, left and right side, and based on data, that data, we will decide the movement of rover to move the rover in a straight line. Based on that data, we will make the rover to move in a straight line. So let's start. First, we will make the Python files in the first part of the video. In the second part of the video, we will be implement on the physical environment, physical hardware, and we will use the ROS environment and how can we will call the Python nodes and the lidar data will extract from the rover. And you have seen the first part of the video how can we make a rover. So the same rover we will be use, and I will show you the hardware part and everything. So first we will make the Python files, then we will be set up the ROS environment, and then we will be implement on the physical hardware structures. So let's start. First, we will introduce our Python nodes to the ROS environment. For that, we are going to start it. We will introduce our node to environment Python 3. Sorry. So we will import the ROS.py module, the Python and ROS communication module that ROS.py is used with the Python with ROS functionality. So we will import the ROS.py module, and then we will take the laser scan from the sensor messages. So we will import these sensor dot messages dot message. As a message, we will check that import from the sensor message, import a laser scan. This lidar is the laser. I will also explain the lidar, how lidar is work. We will check the geometry messages of x, y, and z. And x, we will take the linear velocity. On z, we will take the angular velocity, and that velocity will send on the to rover, and the rover base will movement based on that command velocity. So from geometry messages dot message import twist message. Twist is a type of messages of geometry messages uh, that we mostly use for the command velocity as a linear angular velocity, and it is sent to the rover physical hardware to the motor encoder. And we will also import the math, as math will use to convert that sensor angles to Cartesian coordinate system. For that, we will import the math function. So first, we will initialize one publisher. The publisher is actually, we will publish our velocity command to that topic. And for that, we will publish set up the publisher. We'll initialize the publisher. ROS.py Dot publisher. You can give any name to that topic, and that topic we will send the command velocity, and that command velocity will convert it to the speed of the encoder, and based on that encoder will move, and the rover will be completely rover. The report base will completely move based on that command velocity. So CMD. Command well. West. Size, we will send a quiz size of 10. We will send 10 messages at once a time we can send. And we will initialize one variable that is called a matrix, a list of metrics. We will store the ranges value we take from the Lidar, and it will store in a matrix, and that ranges value distance will be coordinated in coordinated system of distance, and that distances in the matrix. After that, we will take the averages of that all of the distances, and based on that average distance we will move the rover. We will control the movement of the rover. So we will first matrix. We will take 5 angles from left side and the right side, and we will have one for loop, and that for loop will be iterate through these 5 angles. So we will declare one variable that will be number of angles from one side. There will be a 5, and from the left we will take one start angle from where that iteration will start. For that, we start one left, give a start angle of from the left side. That is left angle is equal to, we will start from 178. You have to understand why I take 178 as a start angle. I will show you the the lidar structure, how it is the scanning around 360-degree. Actually, lidar scanning around 360-degree, but it is the lidar RPLidar A1 especially, it is scanning with the resolution of 0.5 degrees. So if you divide 360-degree divided by 0.5 degree resolution, then you will get 720 places of angles around that 360 degrees. So from that, that's why we take 178 as the left angle. And if you want to understand more about that, why we take that 178 as the angle, and you have to understand the basic structure of RPLidar. So, and from the right side angle, we will also take one start angle, that is right side angle, that will be equal to 538. As I already told you that lidar will scanning around 360-degree with 720-degree angle positions, and with 5.5-degree resolutions. So the angle will increment with 0.5-degree resolution. We will declare 2 variables. One will be the right distance and the left distance. Based on that right distance and left distance, we will give some conditions, if else statements, and that condition will apply based on that right distance and the left distance. So right distance, we will initialize this, declare it. two variable left distances is equal to 0. And as I have told you that from the matrix, we take two average distance. One is the right average, and that will be the final value that we will decide for the moment. Right average is equal to 0, left average. We will declare two variable. There will be two matrix, and there will be two loops. One loops for right side angles as the rover is moving between two walls. So we will on the left and the right side, and we will take two distances from the right side and the left side, and we will take two average distances from the left side and the right side. And based on that average distance, we will move and control the rover movement. There will be callback functions. Callback function is very important part of if you are using the Python nodes for the actually, callback function is the function that will always call when there is messages we get from the Lidar or anything, and that based on that messages we will we will call that callback function. Every time we will call that callback functions if any changes occur around that angle size. So there will be two global metrics, global variables. We will declare the global variables. Again, for every loop, we will declare the global variables. Global angle 1. Angle 1, the global. Sorry. Angle increment. Angle increment. There will be two for loops for both sides. For I in range, the RPLidar scanning range. Number of angles, we have number of angle 5. It will be in to iterate over the angles, we will increment through 1 every time. First, we will take for the angle for the current iteration. Left angle. Yes, this is the angle for the current iterations. It will iterate over the that is multiplied by increment angle. Every time the angle will be incremented by 5-degree resolution. As above we have declared is by 0.5 degree. So it will be increment with 0.5 degree increment. We take one range for that current angle, and we will give that range a name range 1. As if you take the RPLidar data distance range, and that range is in a distance and in meter. So we extract that distance from ranges around the 720-degree resolutions, and a range is the array of least. For one scanning, it will take around 720-degree places distances, and we extract that distances from RPLidar. So message dot ranges integer. We declare the angle is an integer. As a floating point, it will give occur the errors. So will not give it as an integer, and you can give as a slice, but you can't give it as a declare it as a float point. Current angle and the current range distance around on that angle. We will take a new range, and that new range will be equal to that new range will be equal take based on the range one, uh, but will be multiplied by cos 0.5-degree resolutions. Range one math dot cos to convert it to Cartesian coordinate, and also to convert that angle into radian. So if you want to convert it to coordinate system, you have to convert it to radian, and then you will you get a distance of in coordinate system. You will I think you have knowledge about the how you will be get the coordinates system in mathematics. So this is the angle of in radian. As we declare a matrix, we will be append a matrix with a new ranges every time that will be iterate over these 5 angles. The ranges, the distance of in coordinate system, the ranges will be stored in the matrix, and we will check the average of that distances that are stored in a matrix. Append a new range, we will be append, store the new ranges value in the matrix. And you can print that values, but I don't think you need the print of the values. To, to check whether matrix is full with that 5 angles. As with every iteration, we take 5 angles. Number of angles we declared before is 5 around both side, left side and the right side. So to check if the matrix is full, we will give another condition. If the length of matrix is equal to number of angles is 5. So if all of the 5 angles are completed or append stored in the matrix, then we will take the average of the distance. As we are developing this for loop for the left side, the same we will develop the loop for the right side. Left distance, we will take the average of that left distance as stored in a matrix. Some of them ranges distances in matrix will be divided by the length of the ranges in matrix, which is R5. You can also print this left distance, but I don't think we need this. Matrix. We clear the matrix again. For the new iteration, we clear the matrix. Okay, so the same way, We have the right side for loop, a callback function. In callback function, we have another loop that are for the right side. Uh, so so this is the for loop for the right side. The same for loop we have. I actually, to understand for you people, I have put some commands and also I have print the values to debug. Uh, you need to, check whether my conditions are fulfilling. For that, you have to print uh, that value, but I don't think we need that. Same loop is as I have developed for the left matrix above. For the left side, the same thing is we have developed for the right side. Okay, so as I told you that we are store as a new variable that are considered as a left average and right average. So now we will decide, the moment of rover based on these average distances. As you will be understand from the coding, how can we extract that average distances of right average distance and the left average distance. Based on these left and right average distances, we will decide the moment of rover. There are the robot that are moving between two walls and that take data from the left and the right side. So we will decide the moment. We will declare another function. The name of the function will be decide the moment. Decide the moment, and will be based on that average and left average and the right average distances as an input to this function or argument to these functions. You can say it. So now we will be have another function. We will define it as a define decide, and that function will take two uh, two input as a left and right average distances. You will understand this from the as I have very clearly written everything. You will understand this right average distances. Okay. Sorry. No, we have some variables, and that variables will take the linear x velocity, y velocity, and the angular z velocity. If you want to understand what is this linear x, if you are very beginning in ROS and Robotics and Pythons, that it is very difficult for you to understand this. You have to check some other sources to understand the twist message vector of coordinate system, how x is used for the baseline of rover. and a y component of the coordinates and the z component. So, but I will tell you that the x component used for the linear velocity, the y component is also used for the linear velocity. So we will use like a linear velocity, the straight move forward and the backward move. But the z velocity of the coordinate system of the component of z used for the angular velocities to turn the rover, the boat around its origin. So I actually declare some variable, and this function will be used inside this function. So now we will have two loops if-else statement of Pythons. It will decide uh, the movement of the robot, the robot between two walls. It will control actually uh, to make a rover in a straight line. We will control if the left or right average distance become greater in the specific values we given, and we take as a ranges distances from Lidar. And if it's greater than this, then it will turn left or right. So we have these for if-else statements. And this if-else statement, you clearly seen how it is implemented, but I will tell you more in detail. I will tell you in detail. Third iteration. Actually, what are going on in there in this FL statement? If the left average distance is greater than 1.3, that is ranges distance, coordinated distance, ranges distance from the RPLidar. If it is greater than this of the left side, then it will turn right toward that moment. L, else if the right average distance is greater than this, then it will turn left to control the straight move. Else if there is no greater, we have less than values 1.3 meters from the left and right side, both side, then we will have straight move. In any case, if it become greater than 1.3 meter from the left or the right side, it will move according, else it will move straight. So how we control the rover movement, and also I will show you physically uh, in hardware structure, so you will understand in better way how this Python node working. This is just to view in this part of the video. We are going to view only Python file. And in the next video, we will set up the ROS environment for these Python files, and we will implement on the hardware structure. We have another function that will actually publish that values to the above command velocity topic as we declare in a top. In these functions, we will publish the command velocity to this topic of publisher command velocity. Okay, so this will publish the twist message to the above topic command velocity cmd world. This will publish After that, we have normal every time it will be the main. This file is not imported. It is our main Python node, Python files, and it will be we given this node as a scan values. And we also subscribe to the scan values of the RPLidar. RPLidar have publishing its ranges value an array list on the topic of scan, and that value will be passing to the callback function, and every time the raspberry will spin and it will rotate and will take the messages distance ranges value. So this is our Python nodes that we are going to make that rover, that robot to move in a straight line to control our rover in straight line between two walls. Actually, it's very difficult to control because every time you have a friction on surface, you have some error in the motor internal, components. And so it is very difficult to control the rover in a straight line. But in this file, you will see in physical structure and video and physical hardware structure. When I'm running that rover, you will understand that because of the motor wheels and the surface frictions, it will divert it from its state mode, and that Python files and the RPLidar data will able to make it in a straight line. So thank you to be with me in this whole video. And in the next video section, I will set up the RAS environment for this node, and I will apply these on the hardware on my rover, and I will show you physically live how it is controlled. Thank you.